Keeper 6.5 virtual problems, total and net change. All right, so example 1, it says at time t equals 0, there are 120 pounds of sand in a conical tank. Sand is being added to the tank at a rate of S of t equals 2e to the sine squared t plus 2 pounds per hour. Sand is being used or taken out of the tank at a rate of r of t equals 5 sine squared t plus 3 root t per hour. The tank can hold a maximum of 200 pounds of sand. So part A says find the value of the integral from 0 to 4 s of t dt. Using correct units, what does this represent? So the very first thing I'm going to do is I'm actually going to find the integral. So I'm going to do the integral of 0 to 4 s of t, and this problem is a calculator problem, so I'm going to type it into my calculator. Before I actually type it in, I'm going to store the function s of t, and I'm going to store the function r of t as shown below. Once I have it stored, I can simply do the integral from 0 to 4 s of x dx, or s of t dt, however you stored it. Press enter and you should get 21.1733. In other words, the integral from 0 to 4 of s of t equals 21.173 pounds of sand were added in the first 4 hours. All right. So again, how much was added between 0 and 4 was 21.173 pounds. All right, so next example, same scenario, but this time it says find the value of integral from 1 to 3 r of t dt, and then using correct units, what does that value represent? So again, I'm going to go ahead and plug in my calculator. I'm going to plug in the integral from 1 to 3 r of x dx, or r of t dt, however you typed it in. And then I press enter and I get 14.8782 as shown below. And so I have the integral from 1 to 3 of r of t equals 14.878 pounds of sand were used from 1 to 3 hours. All right, so part C says find the value of 1/4 integral 0 to 4 s of t dt. Using correct units, what does this value represent? So again, I'm going to do very similar to what I've been doing. I'm simply just plugging it into my calculator because I have it stored. I have S of t and R of t stored. It makes this problem a lot easier. So again, I'm going to do in my calculator 1/4 integral from 0 to 4 s of x dx, or s of t dt. And I get 5.2933. So again, the integral from 0 to 4 of 1/4 of that of s of t is 5.293 pounds. And so what does this mean? This represents the average number of pounds of sand added per hour in the first 4 hours. And the reason why I know it's the average is because I did 1/4 of it, and my A and B values are going from 0 to 4. So I'm like adding up all my values and dividing by the number I added up. That's how we calculate average. So again, it's the average number of pounds of sand added per hour in the first 4 hours. All right, so part D says write a function A containing an integral expression that represents the amount of sand in the tank at any given time t. So what you need to understand is that S of t is measuring how much is being added, R of t is measuring how much is being subtracted, but in order to figure out how much sand is actually in the tank, you need to have a starting amount. So at the very beginning of this problem, they told us that we started with 120 pounds of sand. So when I do my expression for A of t, I'm going to start with that 120 pounds of sand, and then I'm going to add on my integral from 0 to t of S of t, because that's telling me how much I'm adding to the tank, and then I'm subtract off how much we're using. So from 0 to t, R of t, I need to subtract that off. And this would be my expression to figure out how much sand is actually in the tank at any given time. All right, so part E says how many pounds of sand are in the tank at time t equals 7. So I'm going to take that expression that I wrote in part D, and I'm simply going to put in 7 as my upper bound. So I'm going to have 120 plus the integral from 0 to 7 s of x dx, or s of t dt, minus the integral from 0 to 7 r of x dx, and I get 104.42. And so A of t equals 120 plus the integral all the way to 7 of s of t minus the integral 0 to 7 of r of t equals 104.420 pounds. All right, part F says after time t equals 7, sand is no longer being used. So that means R of t is now irrelevant. Sand is, however, added until the tank is full. And remember from the beginning it said that the tank can hold a maximum of 200 pounds of sand. So again, from the original problem, we know it's full at 200 pounds. So it says if K represents the value of T at which the tank is at a maximum capacity, write but do not solve an equation using an integral expression to find how many hours it will take before the tank is completely full. Well, at T equals 7, we calculated in the last problem that T equals 7 was 104.420. Now, because sand is no longer being used and only sand is being added, I could take that number and I can add the integral from 7 to whatever number k, whatever time k, which is what we're trying to find, of our S of t, because that was our formula for what was being added. And we just set that equal to 200, since that's the maximum amount that the tank can hold, and then I could solve for k if they wanted us to. Obviously, they told us don't solve it, so this is my expression, and I am done. All right, so example 2 is very similar to example 1, where we're looking at how much something's adding on versus how much something's being subtracted. So in example 2, it says the tide moves sand from Sandy Point Beach at a rate modeled by the function r given by r of t equals 2 plus 5 sine 4 pi t over 25. A pumping station adds sand to the beach at a rate modeled by the function s given by s of t equals 15t over 1 plus 3t. Both r of t and s of t have units of cubic yards per hour, and t is measured in hours from 0 to 6 hours. At time t equals 0, the beach contains 2,500 cubic yards of sand. So part A says how much sand will the tide remove from the beach during this 6-hour period. So again, I need to use the function that's discussing removing sand. And so if you look, that is your R of t. And so I'm going to store my R of t and my S of t like I did last time. And then I'm going to integrate from 0 to 6 R of t, since they want to know how much is actually being removed from times t equals 0 to t equals 6. And I get 31.8159. All right, so my final answer would be 31.816 yards cubed. And notice I always put this little integral symbol for it, like I actually set up my problem first before I actually write the answer. Don't ever just give the answer. Set up the integral equals the answer. All right, so same example, but this time they want an expression for y of t, where y of t is the total amount of cubic yards of sand at the beach at time t. So again, to find that total, you have to have a starting amount, which they told us was 2,500, and then we're adding on s of t while subtracting off r of t, or adding on s of x or subtracting off r of x. And so this would be my integral expression to find the time t. All right, in example 2, part C, it says find the rate at which the total amount of sand on the beach is changing at time t equals 4. So to find the rate at which something is changing, remember that's the derivative. And so the derivative of y of t, which we calculated in part B, the derivative of that is your fundamental theorem of calculus. So that's going to be s of t minus r of t. And so if I want it at time 4, I'm going to do y prime of 4, which would be s of 4 minus r of 4. And so then I plug that into my calculator, s of 4 minus r of 4. I get the approximate answer of negative 1.909 yards cubed per hour. Notice that my rate, or my units this time, is actual rate, is per hour. All right, part D, it says for 0 to 6, for time being between 0 and 6, at what time t is the amount of sand on the beach at a minimum, and then what is the minimum value. So right there, the second they said when is it at a minimum, they're talking about an absolute minimum. So I have to do extreme value theorem to figure this out. So the first thing I need to understand is that in order to find a minimum, I have to find the derivative and set it equal to 0. Well, remember from the last example that the derivative was s of t minus r of t. And so I'm going to do s of t minus r of t equals 0. And I'm actually going to do it in my calculator. So I'm literally going to type into my calculator, solve S of t equals R of t, or S of t minus R of t equals 0 for t, where t is between 0 and 6. Once you solve that, you should get t equals 5.118. So that gives you your critical number. And so remember, with your extreme value theorem, you have to test your critical numbers and you have to test your endpoints or your bounds. So I'm going to test t or y of 0, which I get 2,500 because that's the initial amount. I'm also going to test y of my critical number, 5.118, and y of my bound, so y of 6. And so I did both of those in my calculator, and I got y of 5.118 is 2492.369, and then y of 6 is 2493.277. Now, because they're asking for minimum, I want the absolute lowest number here. And so the amount of sand is at a minimum of t equals 5.118 hours. And that minimum value, that's the lowest value I had, is 2492.369 yards cubed. All right, if you have questions on this, I'll be here to answer questions on Wednesday at 10 o'clock. And also we'll answer any questions on Thursday in class.